Okay, so this is part 3 of the Chapter 17 lectures on thermodynamics. So this is the continuation. And if we watched our video in the cool videos watch section on entropy, we see that according to the second law of thermodynamics, the entropy of the universe increases for any spontaneous reaction. So in order for a reaction to be spontaneous, the overall disorder of the universe must increase. Now keep in mind that the universe, in any sort of thermodynamic system, the universe is defined as being the system plus the surroundings. So we can define the change in entropy of the universe as being the change in entropy of the system plus the change of entropy of the surroundings. And so formally writing it kind of mathematically, that second law of thermodynamics can be expressed as that the change in entropy of the universe must be positive. It must be greater than 0 for a spontaneous reaction. Okay? So, what makes delta S positive or negative? What makes a reaction become more disordered or less disordered? And it's really going to be broken down into 4 different factors. First of which is our state of our system, whether it's in the gas phase, in the liquid phase, in the solid phase. Particles in the gas phase are very disorganized. They have a lot of random motion, and so they can move around. And so since they have all this freedom of motion, they are very disorganized, and we can say that a substance in the gas phase has a very high entropy relative to the liquid phase, where my particles still have freedom of motion, but not nearly to the same degree as they have in the gas phase. So a gas has more disorganization than a liquid, which means a gas has greater entropy than a liquid. And both of those phases are going to have a significantly higher amount of disorder in them than a substance in the solid phase. When I'm in the solid phase, by definition, all of my particles are in a rigid, organized framework where all they're doing is really vibrating back and forth. But there's no rotational or vibrational motion allowed to the or rather, there's no translational or rotational motion allowed to the substance in the solid phase. So as I go from the gas phase to the liquid phase to the solid phase, my system is becoming more organized. Therefore, the entropy of the system is decreasing as I go from the very disorganized gas, high entropy, to the very organized solid with a low entropy. So for an example, I can look at the reaction of bicarbonate, HCO3 minus, in the aqueous phase, reacting with a proton, H plus, in the aqueous phase. When those two react, it produces a carbon dioxide molecule in the gas phase and a molecule of water in the liquid phase. So I've gone from 2 particles in the aqueous phase to 1 particle in the gas phase and 1 particle in the liquid phase. Now the gas phase has considerably more entropy than any of my other phases. And so we've got the aqueous phase here. Oftentimes we consider the aqueous phase as kind of being somewhere between the gas and the liquid phase in order of disorganization. So we've gone from 2 aqueous phases, which are mostly disorganized, to a system with a gas particle, which is extremely disorganized, has a very high entropy, and a liquid, which has relatively large entropy. So in this system, chiefly because I'm creating this particle in the gas phase, I don't have any gas phase particles on the reactant side, chiefly because I've created this gas phase particle, we can expect that this chemical reaction is going to be more disorganized on the product side than on the reactant side. So we could say that the change in entropy, delta S, would be positive for this reaction. It's becoming more disorganized as it progresses, and I produce more of those very disorganized gas particles. So our state is our most important property that affects our delta S value. Now, another important thing is the number of particles that are present in the system. This is going to affect the disorder of the system. As I increase the number of particles present, there's more ways that I can arrange those particles, and so it's more randomized and there's more disorder to the system. So as I increase the number of particles in a reaction, I'm going to increase the disorder of the system, all phases being held equal, assuming we're all in the same phases on either side of the reaction. As I increase the number of particles, I should become more disorganized. So for example, in this reaction, where I have two C2H3s in the gas phase, that is ethane, reacting with 7 molecules of O2 in the gas phase to produce 4 molecules of carbon dioxide and 6 molecules of water, both of them in the gas phase. If I look at this reaction, I have 2 plus 7, I have 9 particles in the gas phase on the reactant side. On the product side, I have 4 plus 6, I have 10 particles on the product side, all in the gas phase. So since these are all in the same phase, they're all in the gas phase, the side that has more particles is going to be more disorganized. So the entropy of the products is greater than the entropy of the reactants. So as this reaction progresses, delta S is positive. There is an increase of entropy in this reaction because I've increased the number of particles. Now temperature has a significant effect on entropy. Well, temperature is a measurement of the average kinetic energy of my particles, how much my particles are moving. If my temperature is high, my particles have a lot of kinetic energy, and they're going to be moving around a considerable amount, which means they're going to be very disorganized and the entropy is very high. So at high temperatures, when there's a lot of random motion of particles, the entropy is high. If the temperature is low, and my kinetic energy is low as a definition, then my particles are not moving very much. There's very little disorder. The system is very organized, and therefore the entropy is low when the temperature is low. So as temperature increases, entropy increases. And our last factor that affects our change in entropy will be the molecular complexity. And this is probably the most nuanced of the factors. It's definitely the most difficult to kind of see immediately. But let's look at this reaction here, where I have H2 gas reacting with I2 gas to make 2 molecules of HI gas. Now, in this particular reaction, I have 2 particles in the gas phase on the reactant side. I have 2 particles in the gas phase on the product side. And so, according to my first and second factors, I'm okay here. I have the same number of particles in the gas phase on either side. But it turns out that the right-hand side is a bit more disorganized than the left-hand side. The products are more disorganized here than the reactants are. And that's because my products have a bit more of a complex structure to them than my reactants do. Let's look at these 2 markers. So let's say I have 2 markers like this, and this is a terrible example. Imagine I've got a particle, and if I have 2 identical particles and I arrange them next to each other, there is no preference on my orientation. It still sees it head to head no matter how my particles are arranged. But as soon as I have an HI here, now both sides of the molecule are not equal, and there's different ways that I can arrange my particles. So in other words, I could have things like this. So H and I arranged like that. I don't see any difference here, versus I can see a difference between this and this. The positioning of my hydrogens and my iodines, since I can kind of change those positionings, either having the iodine next to the hydrogen, or having the iodine next to the iodine, or even reverse, I with the H's next to each other. All three of these are different states, but with my H2 and my I2, no matter how I arrange them, and it still sees the same thing. It doesn't matter if I'm like that, or if I'm like this, I still see it the same way. So because I have this extra complexity to the HI molecule, and they can see each other from different orientations, two HIs will be more complex than an H2 and an I2. So my reaction there, H2 plus I2 giving me two HIs. Since the products have a little bit more of a complex structure than my symmetrical reagents, these products are more disorganized, and this entropy of the products is therefore greater. So as this reaction progresses, the delta S is increasing. Delta S is positive. Let's look at three more examples. So this is example 17.19 from your textbook. This is in the back of the chapter. And if I look at part A of this problem, I have a aluminum 3 plus in the aqueous phase reacting with 3 aqueous hydroxides to produce 1 solid phase aluminum hydroxide. So in this reaction, I have 4 particles in the aqueous phase becoming 1 particle in the solid phase. The system is becoming more organized because I'm decreasing the number of particles and I'm changing my phase from aqueous to the solid phase. So for both of those reasons, for this reaction, delta S is decreasing. The disorder is decreasing as the reaction progresses, and so the entropy decreases. In my second reaction, I have solid calcium carbonate, so this is calcium carbonate in the solid phase reacting to produce calcium oxide in the solid phase, and a molecule of carbon dioxide in the gas phase. So I've gone from 1 particle in the solid phase to 1 particle in the solid phase plus 1 particle in the gas phase. I've both increased the number of particles. I've gone from 1 to 2. And even more importantly, I've gone from a very organized solid to the extremely disorganized gas. So this reaction, we can expect that the change in entropy will be positive. The disorder is increasing. This third example, I have magnesium solid reacting with aqueous calcium 2 plus to produce aqueous magnesium 2 plus and calcium in the solid phase. So I've gone from 1 particle in the solid phase and 1 particle in the aqueous phase to one particle in the solid phase and one particle in the aqueous phase. I haven't really changed very much this reaction. I really only changed who the charges are. And so functionally, we're going to see that there's not going to be very much change in the disorder. The entropy change is going to be about 0. So this will finish up part 3 of our videos on thermodynamics, chapter 17.